Hello friends, and welcome to yet another lecture on chemical engineering thermodynamics. I am Professor Arvind Prasad, and today we will be studying about properties of ideal mixtures. For this we need to first understand what is a mixture. Well, we get a mixture when we take components of different species and mix them. As we can see in our right, we have M1 and we have M2 and we are mixing it to make a solution M in the beaker. For the solution M in the beaker, the property M can be written as a function of T, P, N1, N2, N3 to Ni, where T is the temperature of M, P is the pressure of M, and N1, N2, N3 to Ni are the mole of 1, 2, 3 and species I in the fluid. Now, the change in property M of the fluid can be written as dou Nm by dou T into dt, that is change in property with respect to temperature, dou Nm by dou P into dP, that is change in property of the fluid with respect to the pressure, and finally dou Nm by dou Ni dNi T, P, Nj held constant. Now this requires a certain amount of clarification. The last differential is nothing but summed over the total number of species I in the mixture. Well, if we opened this summation, the first differential would look something like dou Nm by dou N1 T, P, Nj dNi, where Nj are nothing but N2, N3, N4 till Ni held constant. It means that differential would mean it's the change in property of M with a small addition of N1. Now the next differential naturally which would follow would be dou Nm by dou N2 into dN2 T, P, Nj constant, where Nj now would be N1, N3, N4, so on so forth till Ni. So the second differential would be dou Nm by dou N2 into dN2, that is change in property with small addition of N2 at constant temperature and holding the other moles constant. Now this differential or this summation would be written all over all the components. Now this differential has a special name. Dou Nm dou Ni T, P, Nj dNi is represented as Mi bar, where Mi bar is the partial molar property. The partial molar property of a species I in a mixture is the change in the total property of the mixture to small addition of the species. Now, for ideal fluids, the partial molar property in the mixture is nothing but it is equal to the pure property at the same temperature and pressure of the mixture. So the partial molar property of a species in a mixture is equal to the pure fluid property at mixture temperature and pressure. Now, once again, we come back to the same beaker and conical flasks. Now here, if ideal fluids are mixed at constant temperature and pressure, it means M1 and M2 both are ideal. Then we have the total property M, that is N into M, where N is nothing but the total number of moles. N into M at Tp, that is at a fixed temperature and pressure, is equal to summation of Ni Mi Tp. Note here, since it's an ideal fluid, Mi bar has been replaced with Mi, that is the pure fluid property at temperature and pressure of the mixture. Note, MITP is property of the pure fluid at temperature T and pressure P. If we divide it by N, we would get M at Tp is equal to x1 M1 at Tp plus x2 M2 at Tp for this system. Therefore, we can write that the internal energy of an ideal mixture at a temperature T and a pressure P is nothing but the summation of Xi into Ui, where Ui is nothing but the pure fluid I internal energy at temperature and pressure. Now the enthalpy at T and P can be written similarly. What all this mathematics exactly means? Well, let's take a small narration behind it. Let's assume that we have two gases, oxygen and nitrogen. We have 2 moles of oxygen and 2 moles of nitrogen each. Their temperature and pressure are the same. For example, let us assume their temperature is 25 degrees Celsius and their pressure is 1 atmosphere. Now I would, for simplicity, round off the CV, that is the specific heat at constant volume, to 20. That is 20 joule per mole Kelvin. Now, the internal energy of oxygen is going to be 2 into 2 into 20 multiplied by 25 minus 0, where 0 is nothing but the reference temperature. Now 2 into 25 makes it 50 and 50 into 20 makes it 1000. Similarly, 1000 will also be the internal energy of nitrogen. Now, the internal energy of nitrogen and oxygen per unit mole will be 500. Now, let's do something. Let's mix the oxygen and nitrogen. If we mix them, obviously, we should get 4 moles. Now, but when we mix them, what will be their internal energy? Their internal energy is going to be the internal energy of oxygen, that was 1000, plus the internal energy of nitrogen, that was 1000. So finally, we will have the total internal energy as 2000. Now, 2000 divided by 4 makes it 500. Now, this is very much equal to X1, that is the mole fraction of oxygen in the mixture, which will be 0.5 into 500 plus X2, which is 0.5, and which is nothing but the mole fraction of hydrogen in the mixture into 500. So, the final mixture internal energy is going to be 500, as we can see, and it is nothing but summation of Xi into the internal energies. Similar reasoning can be written for internal, like we have done for internal energy. The similar reasoning can be done for enthalpy too. And with this narration or an example, I can say, I have shown you a method which very clearly says that how do we find the mixture internal energies or the mixture enthalpies of an ideal mixture. Now, one thing should be noted. What is an ideal mixture? Ideal mixtures are mixtures which do not have any residual properties. Now, what do we mean by that? Now, remember, if I took the difference of UTP to summation of xi ui tp, I would get 0. If I took HTP and from it subtracted xi hi tp, I would get 0. Now, the difference is nothing but known as the excess property. The difference is known as, because on the LHS you have the mixture enthalpy or the mixture internal energy, and on the right side you have nothing but the summation of the mole fractions and the pure fluid enthalpies. Therefore, we say that the internal energy of mixing is 0 in case of ideal fluids, and the internal or the enthalpy of mixing for ideal fluids is 0. It is not 0 for non-ideal fluids. This should be noted. The only difference between ideal fluid mixture and a non-ideal fluid mixture is a non-ideal fluid mixture is going to have excess property. That is, the property of the mixture when subtracted with mole fractions into the partial properties will have a value. To further explain this, let's take the example of volume. Let's take the example of volume of a mixture that is ideal. Now let's assume water and ethanol, they are ideal fluids. Let's take 25 ml of water and 25 ml of ethanol. Mix them. Now if I get the total volume after mixing as 50 ml, it means the fluid or the mixture is an ideal mixture, because there is no volume of mixing. The final volume and the initial volume are the same. To start with, we had 25 ml of water and 25 ml of ethanol. And when we mixed it, we got 50 ml of mixture. So there was no change in volume after mixing. Now, what if water and ethanol were non-ideal, form non-ideal mixtures? In that case, if I took 25 ml of water and 25 ml of methanol or ethanol and mix them, I wouldn't get 50 ml of mixture. There would be difference in the final volume and the initial volumes taken. Now, this is an example of a non-ideal mixture. And if we do this experiment in the lab, we will find a volume of mixing or a difference in the initial volumes taken and the final volume of the mixture. We will find this difference for water and ethanol. Similarly, we will find it for water and methanol. Similarly, we will find it for water and sulfuric acid. Now, one interesting thing about mixing water and sulfuric acid also is that apart from having a volume of mixing, that is, the final volume not being equal to the initial volumes of water and sulfuric acid being taken, it would also be found that as we mix, heat of mixing is evolved, which means that the final enthalpy is not even equal to the initial enthalpies, because there is a difference in enthalpies of the mixture and that of the pure components taken, you had heat evolution. Now we get back to ideal gases. When two ideal gases 1 and 2 are mixed, there is a change in entropy, or there is an entropy of mixing. Let's see, how do we find it? Let the first ideal gas 1, let its change in entropy be ds1 is equal to dH minus V1 dP. Dividing this equation with T, I have made a slight mistake here. I should have put T here. Pardon my mistake. You have T here. Yes. Let's get back to the slideshow. Yes. We all know that ds1, T ds1 is equal to dH minus V dP or V1 dP. Now, if we divide it by T, we will get ds1 is equal to Cp dt by T minus R over P dP. For a constant temperature process, this is what we get. And for an ideal gas too. Now the change in entropy, ds1, is going to be equal to minus R ln partial pressure of 1 at temperature T divided by the pressure of the mixture. Now when we mix two ideal gases at constant pressure and temperature, it should be noted that the final temperature and pressure of the mixture is going to be same. But the individual components in the mixture are going to have partial pressures. That is, the pressure that they will have in the mixture will not be pressure P, but it will be their partial pressure P. Therefore, the change in entropy is nothing but minus R into ln to start with what is the initial pressure of the component 1 in the pure phase, which is nothing but P, to the final pressure it would have in the mixture, that is P1 bar, that is its partial pressure. Therefore, we can write delta S1 is equal to minus R ln of Y1, where Y1 is nothing but the mole fraction of component 1 in the gas mixture. The entropy of mixing for ideal gases 1 and 2 is therefore delta S mixing is equal to Y1 delta S1 plus Y2 delta S2, which is nothing but minus R Y1 ln 1 plus Y2 ln 2. If we had a mixture of I components or I species, it would be nothing but minus R summation over I yi into ln yi. There we go. So the entropy of an ideal gas mixture would be now summation of yi into Si, where Si is the entropy of the pure species I at temperature T and pressure P of the mixture, minus R summation I yi ln yi, where this is nothing but the entropy of mixing. As we can see, the entropy of mixing or the internal energy of mixing for an ideal fluid is 0. If we take the difference of the LHS and the RHS, we get a 0. The enthalpy of mixing too is 0. But the entropy of mixing for an ideal gas mixture is not 0. We get it as minus R summation yi ln I. Now this is a positive number. The entropy of mixing of ideal fluids therefore can be written as STP summation xi si Tp minus R summation I xi ln xi, where xi is nothing but the mole fraction. Now the Gibbs energy of mixture of ideal fluids GTP can be written as HTP minus T into STP. Now HTP is replaced as summation xi into hi, where hi is nothing but the enthalpy of the pure species I minus T into xi si Tp, where si is nothing but the entropy of the pure fluid I plus Tr summation xi ln xi. As we can see, there is Gibbs free energy of mixing too. So the Gibbs free energy of an ideal fluid is nothing but the summation of the mole fractions of species multiplied by their pure Gibbs free energies at the temperature T and the pressure P plus T delta S mixing. This was all about knowing the properties of ideal mixtures. This understanding helps us in deriving equations like the Raoult's law. Because in Raoult's law we assume that the liquid mixture and the vapor mixture in equilibrium with it, both are ideal. The liquid mixture is an ideal liquid and the vapor mixture is nothing but a mixture of ideal gases. Now we can apply all that we have studied here in developing the Raoult's law. We shall see this in the coming lectures. But for now, this is all. Hope you have enjoyed this lecture and understood how we calculate properties of ideal mixture in thermodynamics. If you have any queries or any doubts, do write them in the comment box. I shall be glad to attend them. If you have demands for any other lectures to be made on any other topics in thermodynamics, do write that too in the comment box. I shall be only too glad to make them for you. Also, please subscribe and like my channel. This is very essential for me to go on and keep making lectures for you. Have a great day, guys. Keep watching.